All right, so we've been talking about exponential functions and about how to find the equation that goes through them, goes through any two given points. And one thing that can be tricky is that there's usually multiple ways to write the equation that are really equivalent to each other. And the way that you can see that they're equivalent is obviously if you look at their graphs, they're identical. The other way is by using exponent properties to make them match up. And so I wanted to do an example here, looking at our friend. Let's do y equals 1 times 4 raised to the x power. And I'm going to adjust the viewing window here. We don't really need to go up to that big of an x value. Let's just go up to 5, really. And then let's go up to 256, I think is good enough. All right, so that's going to be okay. So what's happening with this equation? Let me make one more adjustment so that they count by ones on the x-axis. There we go. What's going on with this equation here? What's going on is that we are looking at x values that are counting up by 1 and y values that are multiplying by 4. So let me make this work. There we go. And we can let that go as long as we want. Now, there are equivalent versions of this equation right here. One equivalent version would be this. Y equals 1 times 2 squared. And this is maybe not super exciting. 2 squared raised to the x. Not too exciting there because 2 squared is just another way of writing 4. I could have written 2 plus 2 to the x, or I could have written 5 minus 1 to the x. So that probably didn't blow anyone's mind. But if you remember the exponent rule, we have an exponent rule, which is that if you have, let's say, something raised to one power, inside parentheses raised to another power, you can make that into multiplication up in the exponent. So I could take that equation that we just typed in, and I can write it as y equals 1 times 2 raised to, then I multiply the powers, 2x. And you can see that that's also the same. And I want to talk about what these are saying and how they're saying the same thing, but maybe saying it slightly differently. This one is saying multiply by 4 every one step. And this one is saying multiply by 2 twice every one step. And so, in fact, what's interesting about writing it out this way is that it's multiplying twice as often. And if I go into my table and if I ask it to figure out what 0.5 is, you can see that in a half step from 0 to 0.5, it multiplied by times 2. See what I'm saying there? That this is just a half step, and this is multiplying by 2. So this is plus 0.5, another plus 0.5, another times 2. And you can see that as many times as you really want until you're convinced. 1.5 is another times 2. So using that exponent property of raising a power to another power lets me see that multiplying by 4 every one step is the same as multiplying by 2 every half step. In fact, we can do this with lots of other things. We could write this equation as, notice that it multiplies by 16 when you go plus 2 here. And it multiplies by 16 again as we do another plus 2. And that gives me an idea for how I can write another version that's equivalent. Let me see how I can do this. Yeah, there we go. So here's another equivalent version. Another way to write the number 4 is by writing the square root of 16. But another way of writing the square root is by writing the 1/2 power. And another way of writing a power raised to a power is by multiplying them, like I just talked about. So we could write this as 1 times 16 raised to the 1/2 times x over 2. And you can see that that's the same idea. When we wrote it as this, we're saying that we're multiplying twice as often. So every half step it's multiplying by 2. Here we're saying we're multiplying half as often times 16. We could even do a weirder one. You might notice that it's multiplying by 8 every 1.5 steps. So we could say it's 1 times 8 raised to the x over 1.5. And it's going to be the same thing. So in general, what you can do is you can take your original equation of a times b to the x, and you can write it in different ways. You can write it as a times, let's do some different letter, so some multiplier, x divided by, I like to use the letter n or the letter s there. And what this is saying how much do you multiply by every n steps, and then this n is just the number of steps. You might think that this one, the blue one down here, doesn't fit that pattern, but if I remind you that dividing by a half is the same as multiplying by 2, I hope that you are convinced that you're multiplying by 2 every 0.5 steps. So just to finish out this video, what I wanted to show you was an idea of doubling time. And this works the same for half-life. Let's start with just a random exponential function. Let's say it's, I don't know, 35 times 3.5 raised to the x. I have no idea what the doubling time is here. But I know that I can write another equation that is twice as big, and I can find out what the doubling time is by clicking on their point of intersection. So I've got a doubling time of about 0.553. What that means is that an equivalent equation has to be 35 times 2, doubling. And how long did it take to double? It took about 0.553. And you can see that those two curves are exactly identical. And what this tells me is that the number 35 is approximately 2 to the 1 over 0.553. Every exponential equation can be written in lots of different ways. You just need to use exponent properties to make them equivalent, in particular the one that is the power to the power. I'll just do one last even weirder example because why not? We could write it in terms of the tripling time. If you triple 35, you get 105. If I use the point of intersection, it's 0.876. So now I know I can write y equals 35 triples x over point, what is that again? 876. Get into the exponent, 0.876. And you can see that that goes right on top of the other graph. So there you go. Just using that power to the power rule to come up with equivalent exponential equations.